concavity. Just to remind you a little bit about concavity, I'm going to draw through 4 cases. Okay, I think for some reason I have a feeling that I've done this before, but okay. This is where both functions are increasing. Okay, so this is an increasing function, and this is an increasing function. What is the difference between these two functions is the behavior of the tangent. Okay, if I draw a tangent in red at these 2 points that I marked on the graph, the tangent here looks like that, and the tangent here looks like this. Okay, here, this is one tangent, and this is the other tangent. Of course, the section on the left is concave up or down. What say you? I'm saying the sketch on the left is concave up or down? I'm sorry? Sorry, down. The sketch on the right is concave up. Okay? And if you look at the slope of the tangent in red, when it's concave down, as we always move from left to right. Keep that in mind, okay? So we're always heading to the right. And as you move from left to right, what happened to the slope of the tangent? The slope of the tangent is decreasing. Okay? So if the slope of the tangent is the first derivative and it's decreasing, then what happened to the second derivative on this for this sketch? It's the second derivative is the derivative of the first one. It's getting, well, in terms of positive and negative, is it positive or negative? If the first derivative is decreasing, what happened to the derivative function that is decreasing? The derivative of a function that is decreasing is negative. If the derivative is positive, the function is increasing. Okay? If I'm looking, don't look at the graph itself. The graph itself is increasing. Look in red, what happened to the derivative of the graph as expressed by the slope of the tangent? Is it increasing or decreasing? It's decreasing. So what would be the derivative of the derivative? It would be negative, exactly. And this is what happened between, or this is the relation between the second derivative and concavity. The second derivative indicates the concavity. If the second derivative is negative, then the function is concave down. So here we can write, if this is y equal f of x, so concavity of y equal f of x. Okay, this is the title. Okay, so f of x is increasing, f of x is increasing. The derivative here is, of course, is positive. So f prime is positive, f prime is positive. However, f double prime is negative. Okay, and here you can see in red that the slope is decreasing. In other words, the first derivative is increasing, so the second derivative, the derivative of the first derivative, is positive. So f double prime is positive. Okay? Look at decreasing functions. Okay, so we look at this function, like so, that is decreasing, and this function, like so. Okay, so again, we move from left to right, we pick up these points right there. And we draw, first of all, one thing that you realize, both functions are decreasing, right? You agree? As we move from left to right, we go down. But what happened to the tangent? Here, as we move from left to right, the tangent that was negative Of course it's negative because the function is decreasing, so f prime is negative here as well as here, right? But what happened here is the tangent become more negative. In other words, the derivative is decreasing. If the derivative is decreasing, then its derivative, the derivative of the derivative or the second derivative is decreasing. Okay, so we have f double prime is decreasing. And what is this function? This function is concave up or down?
That's concave down.
Concave down. And this function is concave up. Okay. What happened to the slope in this function, the last one? The slope is decreasing or increasing? It's increasing. This was more negative, this is less negative, right? So it's decreasing. It's increasing. If it's increasing, then the second derivative is positive. Okay, look, if you stick a divider right here, okay, what's common to these two is on the left of the pen, both function are concave down. The second derivative in both cases will be negative. If you look at the right, both function are concave up. Even though the top is increasing, the bottom is decreasing, both second derivatives are positive. Okay? If you divide like that, then both functions are increasing above, both functions are decreasing below. So the first derivative above the pen will be positive, the first derivative below the pen will be negative. All right? So this gives you, these four sketches give you all the information about the relationship between increasing, decreasing, and concavity. Sorry, let me rephrase it. Increasing, decreasing in the first derivative, concave up, concave down in the second derivative. One more thing you need to, when you look at the definition, both functions are concave down to the left. Look at the relationship between the tangent and the function itself. Both sketches are concave down. The tangent will be above the curve. That's a definition of concave down. Look to the right where the function is concave up. The tangent are below the curve. This gives you a definition of concavity. So in algebra, you learn that concavity is defined whether the function or the curve is curling upward or curling downward. This is a more precise definition. Okay, a function, the curve of a function is concave up if at any point the tangents are below the curve, except of course when they actually touch the curve. And the function is concave down if at any point in the domain of this function the tangent are above the curve except when they actually touch the curve. All right, so let's write some stuff here. After observing these phenomena, let's write the properties here. So we are in page 3. We're going to write, here's a definition. Okay. 1. F of x is concave up on a certain interval I if all the tangents to the curve of f of x are below the curve on the interval I. Okay, so concave up if the tangents are below are in 2 all we need to do is substitute and say f of x is concave down on I if all the tangents to the curve of f of x are above the curve on I. Okay, so this is a definition. Keywords: concave up or concave down, tangents, and above or below the curve. All right, here's a theorem. Let's write it here. Okay, suppose f double prime of x, the second derivative, is continuous on an interval. Okay, then we have the following. One, if f double prime of x is positive on the interval, then f of x is concave up on I. So this is basically recapping our observation, but this is, in reality it's a theorem. And likewise, if f double prime of x is negative on I, then f of x is concave down on I. Okay. So one way to look at it is if you have a function that does this thing, okay, and let's say this is x equal c, some constant right there. Here, this is concave up, so here we have concave up, so f double prime is positive. This is concave down, so f double prime is negative. What happened at x equals c? Okay, the point c comma f of c right there is called inflection point. And essentially, inflection point is where concavity change. Okay. And what happened, do you think, to the second derivative? If to the left of the point the second derivative is positive, to the right of the point the second derivative is negative, then it stands to reason that at x equals c, the second derivative is exactly 0. Or maybe undefined. Okay, and here comes the definition of inflection point that touches on this definition. That touches on this property, I'm sorry. Kind of. So, here's the definition of inflection point. So here's the definition. Say xy equal c f of c is an inflection point of f of x if the concavity of f of x changes at x equals c. Notice that we don't say anything about the second derivative equals 0, or the second derivative is undefined. There is a parallel definition between, or parallel relationship between critical number and relative extrema. Remember, not every critical number is a relative extrema. I mean, we just had an example where we had critical numbers at -2 and at +2, and they were not relative extrema. However, the reverse is correct. If a point x equal, if f of c is a relative extrema, a relative minimum maximum, then c is a critical number. In other words, c has derivative equals 0 undefined. Same thing will be here. If you know that the point is an inflection point, then probably the second derivative has to equal 0 undefined. But if the second derivative equals 0, or the second derivative is undefined, it does not guarantee that you have an inflection point. So it's not if and only if statement. The same thing as we had with the first derivative and the relative extrema. Here's a theorem that addresses this issue. Okay, so we're going to say that the following: if f of c is an inflection point, so it's given that we have an inflection point of f of x, then f double prime equals 0, or f double prime is undefined. Again, notice how it's parallel to the theorem on the first derivative. Here's a note similar to the note I gave you when we learned about the first derivative. The above is similar to Fermat modified theorem. And what we learn in Fermat theorem, we said if f of c is a relative extremum, then f prime of c equals 0, or f prime of c is undefined. Okay, and the second note is what I said after that, that having f double prime of c equals 0, or f double prime of c undefined, does not guarantee the existence of an inflection point. In the same manner that having f prime equals 0, f prime undefined does not guarantee the existence of a relative extremum. So it's all related to each other.